Everyone. Today we will continue with lecture 20, which is about optimization problems. Lecture 20 is about maximizing or minimizing a certain quantity. What does it mean to optimize? Optimize meaning that we are looking for the best option. For example, for profits, I want to maximize the profit. Costs, I want to minimize the cost of my commodity. So to optimize means we're looking for the best option, which is either you maximize something or you minimize something else. And this is equivalent to finding an absolute max or an absolute minimum. So for any problem we are dealing with, we are gonna pretend that we are finding the maximum or the minimum points of a certain equation or a function. And we do this using the first derivative test. The first derivative test used to say that I need to set the first derivative to 0 or does not exist, and then I find the critical numbers, and then I check the intervals using the first derivative test. Some helping tips. First, you need to read carefully. You need to draw a diagram if possible. If he's talking about an area of a cube, you draw the cube. If he's talking about a volume of a cylinder, you draw the cylinder. Then we determine any quantity Q he's talking about and he wants to minimize or maximize. If he wants to maximize costs, we're going to give it a symbol C and we'll say he wants this maximum. Express Q in terms of the relevant variables. We're going to be using equations to try to minimize variables as much as possible. Then we will use geometry or algebra to eliminate variables. We need to have only one variable that we can differentiate, and then we will find the absolute maximum or minimum using the first derivative test. And we need to check that it is either maximum or minimum. Let's take example 1. Find two non-negative numbers whose sum is 6 and product is maximum. So the two numbers, I'll call them x and y. Whose sum is 6, I found my first equation, x plus y equals 6. And then I need to get one of them in terms of the other, because remember, I need to have only one variable in my equations. So I got y equals 6 minus x. Then he said the product is maximum. This is the quantity that I want to optimize, product P. So I said that the product P, I called it here Q, equals x times y, and then I substituted with the y value that I got in here, so it's x 6 minus x. Now I'm doing the first derivative test. First derivative test, I'm going to differentiate this, so it's going to be first derivative second plus second derivative first, or simply I just say it is 6x minus x squared, so the derivative will be 6 minus 2x, and I set it to 0. And I solve, and I found that x equals 3. Alright, so at x equals 3, we think that the product is going to be maximum, but I need to check. How to check? If I found that the interval before my critical point 3 is increasing, then decreasing, then I'm sure that I have an absolute maximum. So let me try. X less than 3, I just assume to have any point. I use 2. Someone can use another value. Any point in this interval. Substituted, I found it positive value. Positive value means increasing function. And then at x greater than 3, the derivative of any point, you just choose any point greater than 3. I chose 4. I found it a negative, so it's decreasing. A function that's increasing then decreasing. Therefore, at this point in both intervals, x equals 3 is an absolute max. The last step is that I substitute x equals 3 in my equation to find the value of y that he wants, which is equal 3. Let's take another example. Find the dimensions of a cylindrical can R and H. So what is required is R and H of fixed volume. Here comes an equation, V equals 400. A fixed volume of 400, which minimizes the cost of the metal to manufacture the can. So the cylindrical can is made of metal and I want to minimize the cost. Alright, let me draw it. Here is my cylinder. Here is my area. My area is going to be the two circles, which is 2 pi r squared, and then the body, which is 2 pi r h. And here's the equation of the area, which I want to minimize, because costs usually relate to area. I also know the volume of the cylinder to be constant and equal 400. Do I have any constraints in my domain? Yes, the radius have to be greater than 0. In order to have a cylinder, the radius has to be greater than 0. So this is my equation. The volume equals 400 equals pi r square h. The second step, I get one variable in terms of the other, so h equals 400 over pi r square. Then I check my objective to minimize the area. So the area, A dash, I have to set it to 0. So this is the area. It's 2 pi r square plus 2 pi r h. And then I'm going to substitute with my variable in order to have at the end just one variable. And here is my equation. And the last form of my equation is equal to 2 pi r square plus 800 over r. So here I have one variable which is r. So I'm going to differentiate dA by dr, or A prime or A dash. So it's going to be equal to 4 pi r. Don't forget that pi is just a constant. Minus 800 over r squared, and I set it to 0, and I solve for r, and I found that r is equal this quantity. That's not it. I need to check. So I'm going to check. I'll choose any point smaller than the r value, all right, and I found that it is negative, so it's decreasing. And then I will substitute in the derivative with r greater than the critical number, any point I want to substitute with it, and you're going to find that it's positive, so it's increasing. So this means that at r equal cubic root of 200 over pi, this is the minimum. I just substitute in the equation to get the height. Last example. You have a box with a square base and open top, and it must have a volume of 32,000. I have my first equation. Volume of an open top square base box. Find the dimensions of the box. So he wants the dimension that minimize the material used. Remember, material has to do with what? With the area. Okay, so I let the x be the length of the base of the box and h the height. So this is h, and then I have this is x, and I have the inner dimension x as well, because this is like a box. So the volume is 32,000. He said that the volume must be 32,000. So what is the volume of this one? A volume is area multiplied by height. So the area of the square box is x squared, and h is just the height h. And then I'll get 1 in terms of the other to have only one variable. It's required to minimize the area, so I have to get A dash or A prime equals 0. Right now, I'm going to try to figure out the area. The area will be, this is an open top, so I don't have this. So the area will be the area of the below base, which is a square, which is x squared. And then I have four sides like this one and that one. Four sides, okay, of xh, x times h, like here, x times h, and this is x times h. So I have four sides of x times h, so here it is, and then I will substitute h equals the 32,000 divided by x squared. So here it is. So now I have only one variable, which is in terms of x, and then I will set the derivative equals 0, and I solve, and this is the value of x equal 40. I can just say that x equal 40 will be optimized. I need to check. So I just get any point between 0 and 40, because the domain starts as 0, and you'll find that A dash is decreasing, it's negative value, and then again I have to check any point greater than 40 in the A dash equation. You're going to substitute in the A dash equation, which is this one, and you will find that it will give you a positive value. Then so it's increasing. Any decreasing then increasing function, just draw it. It is decreasing then increasing, so you're going to have a local minimum. So the dimensions is 40 by 40, because it's a square base, by 20.